Thanks for joining today's webinar, where we are ready to introduce the HydroGeoSphere Interface, a new graphical user interface for HGS that's available through GMS version 10.8. This has been a long time coming. HydroGeoSphere, of course, is a Quanti's integrated groundwater surface water simulation or modeling engine. And for many, many, many years, our users have been asking us to develop a graphical user interface. Well, one is finally available. We've been working closely with Aquaveo for over 2 years at this point. And with the release of GMS version 10.8, it is now possible actually to build hydrogeosphere models using the HGS interface right in GMS. So GMS, of course, was developed, has been around for quite a long time and is essentially a groundwater modeling interface primarily used for mod flow, but Aquaveo has adapted their existing graphical user interface and it now can be used to develop HGS models. So before getting into its capabilities, I'll just quickly note for everyone that if you want to use this interface, you will need a version or a working license of HydroGeoSphere as well as a working edition of GMS version 10.8. It also requires an additional add-on module called the HGS Interface, which is available through Aquaveo. So having both of these, or I guess three working pieces, a license of GMS, a license of HydroGeosphere, and a copy of the HGS add-on module will get you up and running, and you can build these HGS models and run through this exact same demonstration project that I'll be showing you today. The webinar today is pretty hands-off. What we're going to be running through here is basically an introduction to the HGS interface. We're going to just review some key details about what kind of HGS features and capabilities are supported. We'll do a very, very brief sort of introduction to GMS and the conceptual model approach that is used to craft your HydroGeosphere models. And then just in PowerPoint here, we're going to look at some basically images. We're going to take a sort of a slow look at some of the key workflow steps that you would experience as you build HGS models within this interface. I also want to cover a couple of sort of advanced topics before we get into a live demo. And those advanced topics are going to include importing AlgoMesh 2D triangular element meshes into the GMS interface, and also just reviewing quickly how you can work with some of the features that are not supported directly in the interface using a blended sort of approach, using the interface alongside the traditional approach of building HydroGeosphere models. And then once we've covered that, we'll get into a live demo here. So let's jump right into things. The HGS interface. It's important to recognize that HGS has a huge, huge feature set. We support, of course, integrated groundwater surface water flow and evapotranspiration, but HGS over the years is also, there's been a wide range of capabilities, including modeling of discrete fracture networks, solute transport, reactive solute transport, density dependent flow, et cetera, et cetera. Not every HydroGeosphere capability is going to be fully supported by the HGS interface, but the core functionality of coupled groundwater and surface water flow with evapotranspiration are supported. And in order to allow you to build these fully coupled groundwater surface water models, we also have full support for the usual, basically the usual components of a conceptual model. Obviously, you'll be able to define initial conditions, boundary conditions, property zones, and material parameterization for the groundwater as well as the surface domains. You'll also have a couple of really easy to use windows to help you set up things like your simulation control options, numerical convergence criteria, et cetera, et cetera. And as I mentioned before, there are many advanced features to HGS that are not supported directly in the interface, but you will be able to use the interface as a starting point to help you implement some of those more advanced features. And in fact, you can also use the interface to load in the results from some of those advanced features, such as solute transport. Okay, so GMS, when building models in GMS, and this applies for ModFlow as well as HydroGeosphere. Well, GMS uses this conceptual model approach. Within each GMS project, you can basically save a wide variety of data objects that are independent of any individual model. So this means each GMS project can potentially contain a large number of meshes, or as they're known in the world of GMS, U-grids, as well as different feature objects. These are essentially GIS-based data objects, as well as coverages. So in GMS, we'll often convert GIS feature objects, let's say a points data file, into a coverage, which is essentially the same thing. It's essentially just a GIS file, but it contains a bit of conceptual information about the model itself. For example, pumping rates for pumping wells. So the GMS approach is to have a project that can contain a wide variety of these different model independent data products that can all be combined and mixed and matched within the project to create several different versions of your model. And this is true of HGS as well. So every GMS project can contain several different HGS models, and each one of those different models can be based on different meshes and using different conceptual components or coverages to build those models. Whenever we do create a new HGS model within the GMS project, we'll have to select a mesh or the U-grid that will be associated with that model, and then we'll see how we can just basically drag and drop some of these mesh and model independent data objects down, and that those get basically mapped onto the mesh that we've selected, and that forms the basis for the HGS model. Okay, so let's just take a quick run through of some screenshots basically that will show some of the key steps and key capabilities of the HGS interface. And just to also clarify, this is a bit of a weird webinar that assumes that you have a little bit of knowledge of HGS. It also assumes that you have a little bit of knowledge about GMS. I totally understand that that's probably not the case for most of the people in the room. You may have some experience with one or not the other. I think that's probably the most common experience, or the most common person in this type of meeting. So I'll just point out that Aquaveo has a ton of training material to support GMS users with core GMS functionality like building meshes and mapping coverages to models. Um, a lot of that training material is not really specifically focused on how this would be done for HydroGeoSphere, but the overall GMS workflow borrows from the same types of workflow steps that you would use to build a ModFlow model, for example. Um, so there's plenty of material out there to support the general GMS users. There's also plenty of material to support new HGS users. So we're not really going to get into too many details about the underlying model. Just keep in mind that depending on where everyone's coming from, some components of this workflow may be a little bit they may be a little bit new to different people. So first of all, just a screenshot of the GMS interface here. Of course, we've got a nice visualization window. Depending on the currently active data object, we'll have a number of different GIS style tools to select different model or mesh components and edit them. And then over on the left, we'll have a project data menu. So this project data menu towards the top is where you're going to find a lot of that model independent project data, things like shapefiles, rasters, these coverages which delineate or define the locations of boundary conditions and property zones. We'll have a number of different model meshes. These are all saved into the project data menu. And then further down in this menu, we'll find a simulation data menu. And this is where we really have model the information for individual models. So we'll be able to later on, we'll see click and drag and drop different conceptual items or conceptual data objects down under a simulation to basically map that coverage or map that mesh onto a particular model or an instance of HydroGeoSphere. And I guess something, I'll have a couple of these little asides as we go through the presentation, but if you're not familiar with HGS, HGS supports several different unique domains. And when I say domain, what I really mean is basically a set of nodes that have a common governing equation. So there's a domain for the surface flow or overland flow. There's a domain for subsurface flow. There's a domain for evapotranspiration. Each of these different domains has its own property zones. So in HydroGeoSphere, the way that we typically create or create a conceptual model of our different soil types and things like this is we basically map property zones onto the model mesh, and then we assign a unique material to those different property zones. So we might say, okay, well, zone 1 is a medium sand, and zone 2 is a coarse sand, and zone 3 is clay. Um, the parameters and the actual the parameters that inform the governing equations for each domain, of course, are different. So in the subsurface, we'll need to define things like porosity, hydraulic conductivity, specific storage, whereas in the surface domain, we need to define things like friction coefficients. The HGS interface within GMS here supports basically this traditional workflow that's going to be familiar to HGS users. It just makes it a fair bit simpler to do this. So within the GMS interface, we'll be able to map things, for example, raster files, which delineate property zones directly onto a model mesh. And the end result is basically what's shown here in the bottom. We've basically taken a raster and then just intersected it with a model mesh to apply property zones. So currently in this image, we've got zone 1 and zone 2, zone 1 in blue and zone 2 in red. The next step in this tutorial is to basically select a polygon data object, which again, we're going to use as our basis for intersecting some elements in the mesh and applying them to a third property zone. So we can map shapefile objects as well as rasters directly onto our mesh to help us define the delineation of those different property zones. Once we've defined our property zones, then in the HGS interface for GMS here, we can also define all of our unique materials directly in one of these sort of convenient windows that displays all of the different parameters that we could potentially choose from and define. So we'll see an example of that live there in a few minutes, but basically what's really exciting about this for HGS users who've never had a GUI before is that it tells us exactly what parameters we need to define depending on what type of domain we're actively working in. So here we see a window where we're defining a porous medium material, and so we have to define things like your hydraulic conductivity, specific storage, and porosity. In HydroGeoSphere, given that unsaturated flow is, we perform full 3D unsaturated flow, we'll also have to define those unsaturated zone flow properties. So those can be defined using functions, including Van Gunukten or Brooks-Corey. Again, all of the necessary parameters are listed right here in the window, so it takes a lot of the guesswork out. We can also define the variably saturated flow relationships using tabular values, so saturation versus relative K or pressure versus saturation. So again, this is all going to be familiar to seasoned HydroGeoSphere users. It just makes it a lot easier to kind of actively graphically see the data that we're applying to the model as we build it up. In this next screenshot, we're actually defining a surface flow domain. So we might think of this as land use properties. But again, because we're defining a surface flow domain, it automatically updates the window so that we know exactly what type of parameters that we need to define. And here, finally, we have one material zone for the evapotranspiration domain. And again, all of the different parameters are dynamically updated. So once we've defined all of these materials, we'll basically just map those to some of those predefined zones. So we can see here we've got 3 different porous medium materials, 2 different surface flow materials or land use zones, 1 ET zone, and these are all being mapped specifically to coverages that to 3D cell data sets. So in our mesh, if we back up a few slides here, again, we've got a 3D mesh here that now has elemental property zone values associated with them. All we have to do in order to parameterize the HydroGeoSphere flow domain, whether it's the subsurface or the surface, is basically say, okay, well, all of the elements that contain zone a parameter or property zone 1 will basically associate those with our medium sand material. So once we've finished defining all of our property zones and materials, we'll move on to defining boundary conditions. And so again, for those who aren't familiar with the sort of HGS workflow, traditionally we would have to define a set prior to defining a boundary condition. This is done basically automatically through the HGS interface for GMS here. In GMS, the workflow is to basically, have feature objects. These are GIS-based files, whether they're points, polylines, polygons, arcs, etc. And we use these objects to define coverages. And again, coverages are basically the same type of thing. They're GIS-based objects or CAD layers, but these layers will contain a particular set of information related to our boundary condition. Um, so there are several different types of coverages that are supported in the HGS interface, including boundary conditions, observations, and hydrographs. But these coverages basically define all aspects of our boundary conditions for a hydrogeosphere model. There's no need for you to create a set beforehand. It all happens automatically. And what's really nice is that the type of feature object that you're working with determines what kind of boundary condition may or may not be applied. And so I think we have some images showing that here. What's shown here is just basically a GIS data object, right? A polygon shape file that has a couple of internal polygons and different polylines to delineate different property zones. We've got some points data files or point coverages that delineate the locations of some pumping wells. That's what these red flux nodal dots are. If we were to click on one of those dots after having defined the coverage type as a boundary condition, it will automatically determine what kind of boundary conditions are actually available to us. So as we set the boundary or we set the coverage type from our project data menu, and then once we, for example, double click on a polygon, if that polygon is, or if that data object or that coverage is a hydrogeosphere boundary condition, then the polygon basically tells us what types of boundary conditions can potentially be applied to this coverage type, if that makes sense. I feel like I'm kind of talking around in circles, but again, we'll see a couple of examples coming up here shortly. So polygons here, though, they can be used to define specified head, specified fluxes, rain and potential evapotranspiration, boundary condition coverages. If we were to double click on a point object, then basically we then have the option to apply a flux nodal boundary condition. So this is just a specified volumetric flux. And again, depending on what type of boundary condition we're applying, the windows themselves are dynamic and will be updated to give us all of the different input fields that we need in order to define the nature of that boundary condition. In this example, our flux nodal boundary condition is basically being applied to 4 individual nodes throughout the model domain, and we've applied or we've specified at what depth in the model, so which node sheet that boundary condition should be applied to. We've specified the input type as being a time series, and so that allows us to open up an XY series window where we define that time varying boundary condition. And again, if we were to select an arc or a polyline data object, then this gives us a different set of potential boundary conditions to use. So polylines or arcs can be used to create head, flux, simple river, simple drain, and critical depth boundary condition coverages. So a boundary condition like a critical depth doesn't actually require us to define a volumetric flux or anything like that. And so when we choose critical depth, again, the window is dynamically updated to just expose the information that we need to actually apply, which in this case is just a name. So once we've mapped out all of our different property zones onto a 3D mesh or a 2D mesh in the case of the surface flow domain, and once we've created a series of coverages, which again are just conceptual objects that delineate the location and information associated with boundary conditions, then we can actually create a hydrogeosphere simulation. So we do that just by right clicking in the project data menu and selecting new simulation hydrogeosphere. That's going to create a new element in the simulation data section of this project data explorer, which then allows us to drag and drop different conceptual elements under the simulation. So we'll create a simulation and then we drag our different meshes, our 2D and our 3D mesh, under the simulation as along with however many different conceptual boundary condition coverages we want to apply. And then once we've dragged them down there, we can then move on to defining some some other options about the simulation itself. So for the remainder of these slides, we're mostly going to be seeing windows or capabilities that come about through right-clicking on the individual simulation. Um, so this right-clicking the individual simulation here in the Project Data Explorer allows us to access the materials menu, which we already saw a little bit earlier. That's where we define the material types for our project. It also allows us to access the simulation control menu, where we can define things like initial conditions, output times, numerical convergence criteria, time stepping settings, and things like that. We'll also use this little menu to actually run the model executables, which we'll talk about more in a second, and then read the solution back into GMS as well. So if we right click on a simulation and access this simulation control option, it's going to open up this window. And as I mentioned moments ago, that this window allows us to define a lot of really critical but basic information about the HydroGeoSphere model. We'll be able to define things in the general tab here related to uh, basically, well, we can provide a description of the model, determine whether it will be run in transient or steady state mode, whether it will be run in saturated versus unsaturated mode, whether or not we want to include the optional domains like surface flow and evapotranspiration. We can choose our solver type, things like that. Then we also have a tab for units where we can define our project units. And I want to make a note here that you shouldn't rely on the GUI to convert any units for you. It won't do that. The best practice is always going to be to define all of your model input data in the same units that we've chosen here. It's also important to note that GMS at large can have project units, which may be different than these HGS project units. So again, highly recommend making sure that the GMS interface and the HGS project units match. It's going to avoid any potential confusion or potential, weird things happening with your different data objects. Then we've got a saturated flow and a variably saturated flow tabs, again, just allowing us to toggle on or off different options related to the saturated and variably saturated flow models. We've got a time stepping window, which allows us to define things like our initial time step sizes, minimum and maximum time step multipliers, adaptive time step control settings, as well as our Newton convergence criteria. A simple table where we can list all of our project output times, a menu here where we can define our zones. So for each individual model, we'll basically select one of the predefined 3D or 2D gridded data sets, which allows us to define where our property zones are. And finally, a tab for defining our initial conditions. So again, all the major options that seasoned or experienced HGS users would expect. They're all listed and found here. We can define initial heads based on an arbitrary elevation, based on a depth of water table. We can set initial heads to the surface elevation, or we can use output files from previous model runs as well. Now, before we get into the next steps, which is actually to run the model and then sort of review some results, for those of you who don't have any experience with HydroGeoSphere, I think it's important to note just some basic information about how a HydroGeoSphere actually works. Basically, just like ModFlow, you do need to create a set of text-based input files, which are then going to be translated into model input files, which are then fed into a program that basically solves a system of equations. In the world of ModFlow, it would be one of the many different ModFlow engines, whether it's ModFlow NWT or ModFlow 2005 or ModFlow 6. In HydroGeoSphere, the program that solves the system of equations is actually known as phgs.exe. But in HydroGeoSphere, what we would do is we would typically create a text-based input file. It's known as a grok file. And that grok file is a simple ASCII text file. It's human readable. We would then run a model preprocessor called grok.exe that reads the grok file, executes all of the commands found within the grok file, and prepares the system of equations to be actually be solved. So then the next step is to run PHGS, and then traditionally we would run one of two programs, hsplot or HGS to VTU, which would reformat model outputs for visualization. Step 4 here, not really required at all in the HGS interface for GMS. So the GMS interface as well, it facilitates but doesn't necessarily bypass all of these steps. It does bypass step number 4 entirely, but all of these other steps can be done directly within the GMS interface. So at this stage, we've used the simulation control window to define all of our model options. We've used the materials window to define the material types in our project. We've dragged and dropped conceptual model elements under the simulation, which basically arms the model with all of the information it needs about boundary conditions. At this point, we're ready to actually start running the model and kind of constructing the input files. So this is going to take a couple of steps. What we're going to do first is we're going to right click on this simulation and we're going to actually choose the Save Simulation button. What Save Simulation does is it actually takes any changes that you've made within GMS and it writes those changes to the grok file. So when you click Save Simulation, what it's actually doing is it's writing a grok file automatically in the background for you. So if you ever make any changes to your model and you want to actually push those changes through to HydroGeoSphere, it's really important that you use the Save Simulation button. The Save Simulation End Project button does the exact same thing, but it also saves the current project state of the GMS project files. So once you've saved the simulation, you've essentially created the grok file and you're now ready to move on to the next step, which is running grok.exe. So when we click run grok, it will open up a window and it will automatically initiate grok.exe. And for HGS users, this screenshot here on the bottom right is going to look semi-familiar. This is basically the output that we would typically see in the command prompt, except it's echoed here into a GMS window directly. If everything works as expected, then we should see this normal exit message, at which point we click OK and we move on to the next step, which is to run PHGS. And again, we just right click the simulation and click Run PHGS to initiate this step. It opens up a new window, which also displays the output that you would typically see in the command prompt. And it is also going to show a helpful chart, which actually allows us to review the water balance error as the simulation progresses. There are a couple of little bugs currently with this chart up at the top, but those should be resolved, I think, pretty soon. Actually, the bug that I initially encountered where I wasn't seeing the chart was due to the fact that I was using the latest version of HGS. Currently, we recommend using the October 2023 version of HydroGeoSphere. It's the most stable version of HGS to use with this interface. But of course, we're going to be continuing to fix bugs and improve the interface as we go along. So bear with us in that case. So once the model is run, the next step that we're going to do is read solution. So we no longer have to run hsplot to reformat outputs or anything like that. GMS will handle all of that automatically, but we'll right click and select read solution. And what this does is it basically tells GMS to go into the project folder to identify every individual model output file and to start reading them into the GMS interface. So if you're not familiar with HGS, you may be surprised at the quantity of data that it produces. Compared to ModFlow, we're running full 3D variably saturated flow with evapotranspiration, with surface flow. This just means that we're producing at every node throughout the model domain, probably an order of magnitude or more data than ModFlow would. When we click this button to read solution, it's basically going to read in all of the available geospatial data sets that can be found in the project folder, and those will be saved under an OLF and a PM file. OLF stands for overland flow, so these are all two-dimensional data sets in the OLF section, whereas in the PM section for porous medium or subsurface flow, we're going to have a set of three-dimensional output files. We don't have time today to explore every single data object that you're going to find when you read in a solution, but I'll just point out that I offer a free training session every month, and this is one of the topics that we kind of cover in my Intro to HGS workshop. So feel free to attend one of those if you want to learn more about that as well. But all of the data that we're going to find in this section here, these are basically snapshots of the model state at particular points in time. So we'll be able to, of course, visualize any of the HGS data sets that are produced by the simulation. So things like velocities, head distributions, groundwater surface water exchange, actual evapotranspiration rates, fluxes in multiple directions, et cetera, et cetera. There is a time step picker window at the bottom left here. So if you're running a transient solution that has output time, or many, many different output times, then those will all be listed down here in this time step picker window. So here we see an image of just basically a 2D data set, probably looks like heads throughout the overland flow domain or heads in the surface domain. And here we've got a 3D output. So this is heads throughout the subsurface. In addition to all of the snapshots of model results across the entire model domain, HGS also produces a wide range of time series output files. So there's a lot of data that's going to be produced by default, things like water balance information, boundary condition fluxes, and Newton simulation convergence criteria, things like that. But we can also create coverages for hydrographs and observation points and things like this. So all of those time series outputs that are specific to a particular location, those will all be available in the solution plots menu. So again, GMS should pick up on every available solution plot and load it all in here automatically, at which point you can just turn on or off individual variables and see how the solution changes over time. That's basically a walkthrough of the interface, and I'll do a live demo here in just a minute. But before we get into that, I just want to point out a few things for those experienced HGS users. Most HGS users, we recommend, and internally at Aquanti, we definitely build up all of our model meshes using AlgoMesh. It's a program that has basically the most advanced mesh generation and optimization algorithms available. And a high quality mesh is really, really important for HydroGeoSphere models. HGS models are much more complex than ModFlow models, and they basically we're running a variety of different non-linear governing equations. So HGS models are really complex. They tend to take longer to solve, and that's why having an optimized mesh is really, really important. It's going to help you with faster model runtimes. You can still use AlgoMesh to develop your meshes. All you would need to do is take a few extra steps to convert the AlgoMesh output file, which is an AH2 file, to convert it into a TIN file format, which is supported by GMS. So you just need to add a couple of flags or keywords at the beginning of the file and at the end of the file, and at the point in the file where we basically start listing nodal index numbers. So if you're ever, need a walkthrough of this, feel free to just reach out. I can show you how it's done. It's quite simple. But once you have this 2D triangular element mesh in the TIN format, you can load it into GMS and then use some of the built-in tools to convert that TIN file to a 3D mesh using raster files or any other number of different options to define your soil layers and elevations. And also, I just want to point out that if you right click on a simulation, there is a button that will open the containing folder, which is a quick way of just immediately navigating to the location of the project grok file. Here you can basically switch over to the traditional workflow, which is to modify the grok file manually in order to incorporate some of those more advanced features such as solute transport. And I'll show you how this is done as well. The really nice thing about this is just that the GMS interface doesn't really get in the way of you implementing any of these advanced features. And in fact, after modifying a model to perhaps include solute transport, for example, you can run the simulation directly through the GMS interface and then load the results in when you read the solution. And it will also pick up on any, um, you know, let's say a concentration output files. So you can still review the results of these advanced features in the GMS interface, even though at this stage, in this early beta version of the HGS interface, they may not be fully supported. Another nice thing about working with the GMS interface is that if you do want to use this traditional method of modifying your grok file manually, what you'll notice as you go through a grok file generated by GMS is that all of the selections when we want to identify nodes or elements. The selections basically all happen using node and element index numbers, but GMS has some built-in tools that allow us to automatically identify node and element numbers here in the GUI. So if we select a number of nodes where we want to apply a boundary condition, for example, we can open up what's called the selection echo. It's a small window on the right-hand side of the screen, and it will basically spit out a list of all of the node index numbers. So working with these index numbers has typically been something for advanced HGS users, but now that we have a graphical user interface, it's actually really, really simple to identify node and element index numbers at particular areas of interest. So you can just basically copy this information directly into a text file, do a little bit of post processing to make sure that we have one unique node index number per line, but then we can just take this data and basically adapt it into a node list, which again allows us to implement other features which may not be supported by the interface itself. Um, yeah, so then after having updated the grok file, so in this example, what I've showed is basically a concentration field. So I updated a grok file to incorporate some solute transport commands. What I do then is basically just run grok again and then run phgs and read in the solution. We do not want to save the simulation. If we make any changes manually in the grok file, right clicking and selecting save simulation will overwrite those changes to the grok file. So keep that in mind. But basically it allows us to, as I said before, right, incorporate advanced features that may not be fully supported by the interface. We can still benefit from, for example, the visualization capabilities of GMS to show a contaminant plume in this case. Okay, so this is not the end of the presentation, of course. I'm going to switch over to the GMS interface, and we can kind of take a look at some of those different things that we've just seen. So I have essentially a working or a fleshed out project here. So in this project, we already have defined a 3D mesh. This 3D mesh actually already has some of our property zones applied to it. We've got basically a channel of coarse sand in a mostly medium sand region. And in layer 5 here, we've got a clay lens. So this is just basically an adaptation of the HGS intro tutorial. So this may be familiar to a lot of you. So we've got our three-dimensional property zones already defined. The way that this was done was basically by creating a new cell-based data set. So here we've got a new one where the cell values are based on elevations. But we can easily do things like select all of the elements within this data set. And we could potentially then just change some of the values associated with those data sets. For example, yeah, like just by selecting on any one of these data sets. Oh, first we have to unlock this grid. That's why it's not working here. But yeah, if I select all of these elements, I could say, okay, well, let's reassign all of them to zone 1. And now we've got a single homogeneous property zone. What we could do then is interpolate something like a property raster file, which is what's shown in the background there. We can interpolate that onto one of our new data sets. So this allows us to basically select our data source as well as select the location where we want to define that cell data set. So we're going to apply it to this new data set that I just created. Click OK. It's going to run through an algorithm and map all those data. At which point now we have created a new property zones coverage. So this is a cell-based data set. This is what we're going to be using basically to define our property zones. So this particular demo project, as I said, it's already got our different surface and subsurface property zones delineated. We've also got an ET zones as well. We've got a number of different coverages up here in the top. So we used basically polygon data files to delineate the location of our property zones. We've also now got a coverage for surface flow boundary conditions. So if I double click on this polygon, we can see that we've already applied a rain boundary condition for this polygon. It's at a constant rate of 5.55 e to the negative 7 meters per second. I think it's something like 2 centimeters per hour. If we select any other components of this coverage, for example, the polyline arcs around the edge of this coverage, we can see that I've actually mapped out some critical depth boundary conditions to these locations. So again, this coverage is just a conceptual, element to the project. It's not mapped on at this point to any individual mesh or grid or anything like that. So we've got surface flow boundary conditions, we've got porous medium boundary conditions. These delineate the locations of some flux nodal boundary conditions. And again, they're already predefined here. We've got a time series pumping schedule. Every 6 hours, these pumping wells will turn on and off. Then we've got evapotranspiration boundaries. We've also defined some hydrographs as well as a few observation points, just kind of in arbitrary locations here. But once we've created all of these conceptual project elements, right, all we have to do then is map them onto a pre-existing HydroGeoSphere simulation. So if I right click, I can create a new simulation. Now this simulation here, if I access the simulation control menu, currently everything here is going to be set to the default settings. So we can again change our solution type. We can change how many or what types of active domains we've got. We can change our units. A lot of different options here in terms of how we set up the simulation. I'm just going to close this for now. I'm going to delete this new simulation I just created because I've already predefined a lot of this. So again, here in our simulation control window, we've defined initial conditions already. So an initial head depth to water table 7.75 meters. What we need to do here is map our property zones onto the simulation. So we have all of these 3D and 2D cell data sets that delineate the location of our zones. All we have to do is select those zones or those data sets in order to map the zones to our HGS model. So we just select from any one of those available cell data sets. So again, I've already pre-mapped these out, so there's no need for me to make any changes here. I've defined our output times. I've defined all of our time stepping settings and numerical convergence criteria. So this has all been pre-done for us, so I don't have to waste anyone's time just entering numbers. Once all that's been defined, we would also want to access the materials menu. So again, we can access and change any individual properties. If we wanted to create a new property zone for, let's say, our porous media, we would just basically say, okay, well, this is going to be associated with zone 4, and we can define, again, all of the individual parameters that we need to define that soil type. Now, in this particular project, we don't actually need a 4th zone. But after having defined all of the materials themselves, don't forget that we need to associate every individual material with a particular zone that's been pre-mapped again in these cell data sets. So in our porous medium domain, we have 3 zones. Those have been predefined, zones 1, 2, and 3. And again, just as a reminder, those zones are basically zone 1 in blue, 2 in green, and then if we look in layer 5, we've got a clay zone as well. So that's zone number 3 right here. So all of our porous medium materials have been predefined, our surface flow zones as well. So this basically tells, again, it tells the interface which property zone number belongs with which material that we've defined for this project. And yeah, with all of those changes, right, just a couple of small updates to make sure that our material numbers are properly assigned to zone numbers, potentially make some updates here. Maybe let's change our initial condition to a depth of 1 meter. Whatever changes we need to make, right? So our simulation controls are now set. What we need to do now is map some of our meshes into the model and then map some of these coverages onto the model. So basically what happens now is these conceptual model objects, right, are just being intersected with the mesh that we've selected for this particular model. So we've got surface flow boundary conditions, we've got our ET boundary condition. The pumping wells will slow things down a little bit. I want this model to run very quickly here, so I'm not going to bother mapping those in for this instance of the model. But we've got our observation points and hydrographs, and I think that pretty much covers everything that we need here. Surface, ET, we should be good to go. So we're just going to save this simulation. Takes a moment here. It's updating and writing the grok file. I can access the grok file now by opening the containing folder. And this grok file was just generated just moments ago here, and basically has a fully functioning grok file. So we don't actually have to make any changes here ourselves. So we'll close that up here. We can then run grok, normal exit, everything was successful, and we can now run PHGS. And as we run PHGS, right, our error percent, our water balance information is being displayed up in this graph, and basically HydroGeoSphere will run through the simulation. Now, this should only take about a minute, but I see that we're already 50 minutes into this webinar, so I'm going to abort this model run. I'll close this window, and I'll just open up a version of the model that I ran previously. So this is actually a version of the model that I had manually opened up the grok file and amended the file with some solute transport information. Probably won't do that live with you right now, but we can at least take a quick look at some of the model outputs here. So after having run PHGS, again, if everything runs successfully, then what we would do is right click and then read the solution in. Keep in mind that this will overwrite any pre-existing information that we have from prior model runs, but that's okay in this case. So it's just reading in all of the different data files that are associated with this particular instance of the HydroGeoSphere model run. As you can see, lots and lots of different data here. If I expand both of these folders, we can see that there's just lots and lots of data. And again, these are all just basically 2D or 3D data sets. So if I wanted to look at some of our OLF data here, what I would want to do is turn off the 3D mesh and activate the two-dimensional mesh. And basically what we have here are concentrations changing over time throughout this model. We've also got, velocities. We've got heads in the overland flow domain. So those don't really change too much. And in fact, I think the contouring would need to be updated for some of these different variables here, because I had basically specified a range. So there we go. There's our heads. If we want to look at some of our porous medium output, we can activate it here. But again, we'll need to make sure that we activate the 3D mesh in order to see the results in the 3D context. You can scroll through our different time steps here. Again, my contours need to be updated. That's why everything's just showing in one color there. So you can see the evolution of heads over time. This model doesn't change too much over the course of a one-day period, but that's basically how you would look at some 3D results. And then I guess the last thing I'll just want to quickly highlight is the solution plots menu. So again, any time series data, whether it's associated with a hydrograph or potentially observation points, or maybe it's just our water balance, storage changes, fluxes associated with boundary conditions. These basically all get loaded in automatically, and we can start quickly and easily comparing different variable data. This chart here is fully customizable. I'm not going to get into that too much today, but you can access, a bunch of options here to configure subplots, modify, just basically modify the chart options. Okay, so yeah, with basically 10 minutes to spare in the hour, I guess that brings me to the end of my quick demo. Couldn't run through the whole thing today, as you'd imagine. It would just be a lot of me typing numbers into fields. But I hope this quick, this quick demo gives you an idea of how the interface works. Of course, Aquaveo and Aquanti, we're happy to help anyone with a software trial. I plan on following up with everyone with a recording of this webinar, perhaps sometime tomorrow, along with a copy of the project itself, so that you can test out some things yourselves. But I guess at this point, I'd like to just open the floor to questions. We do have a couple of people from Aquaveo here today as well, so I think we're well equipped to answer any questions you might have about whether it's GMS or HydroGeoSphere.
Braden, there's a few questions in the chat.
Awesome. Thanks for monitoring those, Michael. Maybe we just start from the top and work our way down. So can users simply use the GMS interface to create UGrids that are compatible with HGS? And the answer to that is yes. You can build your meshes directly in GMS. The HGS does not by any means require a mesh to have been built using the AlgoMesh platform first. HGS should be fully interoperable with any type of UGrid that you generate directly in the GMS interface. And Michael or anybody else from Aquaveo, if I say anything incorrect, feel free to jump in just to correct me, but I'll just continue on now with some of these next questions. Is it possible to visualize particle tracking as well? That's a great question and not something that I've tested myself. I believe the answer is no, actually. So particle tracking in HGS has a particular formatted output files that have not been captured by this initial beta version of the HGS interface for GMS itself. With that being said, though, I might ask Michael whether or not GMS has any built-in particle tracking capabilities that you could imagine potentially intersecting with HGS without too many issues.
Yeah, we do, but we have plans to do some new particle tracking work with another model, and we think that that could be generic enough that we could apply it to HydroGeoSphere in the future. So yeah, I think that would be something that would certainly happen. I
Awesome.
don't know exactly when, but yeah.
Great. Yeah, so I guess the answer maybe right now is not immediately, but something for us to definitely look into for future iterations of this HGS interface. We've got a question from Chris here. Are there plans to add the channel flow domain into the GMS GUI? And does the GMS GUI assume the dual node approach? So for the first question about channels, it's not currently possible. Um, we do plan in the future to expand the number of domains and features and capabilities that the HGS simulation engine supports within the context of the GUI. But as of right now, there's no support for channels or 1D hydraulic features such as, sorry, no fractures, no channels, no tile drains, no wells. And then the GUI does assume the dual node approach for the surface flow domain. In fact, I believe you can set that in the simulation control section. Actually, no, I think, yeah, we hard coded it in. So the GUI will always assume the dual node approach, which is what we recommend. And we don't actually expose an option to toggle it on or off. That doesn't mean that you couldn't use the common node approach, not that we recommend it, but you could just modify the grok file directly to use the common node approach. And then there's a question here from Walter. He found the choose elements between raster surfaces command particularly useful. How can I use it here? Well, the beauty of the GMS interface is that you don't really need to use any commands from the HydroGeoSphere context to select elements. So if you wanted to apply, for example, choose elements between raster surfaces could be used to define the location of a clay lens, for example. That's actually something that is built into the HGS tutorials for this interface. But if we look at the 3D zones, and again, we look at layer 5, this is one potential area where you might want to use that command of choose elements between raster surfaces. But there's a million different ways to kind of get at the same information using the GMS interface. One example here would be to simply select a coverage, let's say a coverage that includes your polygon data file. And then what we could do is we could select a polygon at the location where we want to make those selections, and we can basically select intersecting objects. Okay, so I have to be in plan view to do this, so let's go to plan view. So basically what this allows me to do is I can select individual polygons within this coverage and then intersect the selection onto the UGrid. And right now, since I have layer 5 active, it's only going to select the elements within layer 5, if that makes sense. So to answer your question, Walter, You wouldn't really use any individual command that HGS supports for selecting individual elements or nodes, but the HGS, sorry, the GMS interface has a lot of different tools that allow us to basically graphically select elements at particular locations in order to apply coverages and to define property zones, things like that. Another question is, can HGS simulate in finite elements? And the answer there is yes. So again, in the simulation controls window, this is where you're going to define your solution options. The default option in HydroGeoSphere is actually to run the model in finite element. So if you deselect this finite difference mode radio button, then the model will run using the finite element solver. Okay, lots of questions. On to the next one. Is it feasible to design and implement an integrated subsurface network model aimed at reducing groundwater levels in coastal areas over the long term? Definitely yes. I mean, I'm not going to get into this question in any detail, but HGS is a strong option in terms of modeling engines for just this type of project, and you certainly could use the interface to design the model itself in order to reach those project goals. So yes, but feel free to reach out to me and we can have a discussion one-on-one about how you would go about doing that. And a question about finite element versus finite difference. Since HGS is by default a finite element simulator and GMS works on the finite difference method. Well, GMS, as first and foremost, it's a mod flow. It's a GUI for developing mod flow models. And yes, those mod flow models typically, yes, are based on the finite difference solution method. HydroGeoSphere, we're using GMS here to build a HydroGeoSphere model. It's using a completely different simulation engine, so there's no mod flow involved. It's HydroGeoSphere instead. And again, the default solution method in HydroGeoSphere is that it is a finite element simulator. But HydroGeoSphere also supports options to run the model as a finite difference mode or a control volume finite difference mode. So basically, GMS itself is just a graphical user interface for designing models using a number of different engines at this point. So the HGS engine is a finite elements model, can use finite difference mode as well, though. Okay, on to the next question. Is there any difference in runtime, and can you run multiple simulations through the GUI at once? There may be a slight decrease, or actually I would say a slight increase in model runtimes, but generally the only thing that the GUI does here is it needs to just pull a little bit of information from the water balance file in order to display the water balance error during runtime. So at the end of the day, when you run PHGS here, it's nearly identical in terms of runtime. There's really not much computational overhead in having to display some of that data. So overall, model runtimes should essentially be identical. And can you run multiple simulations through the GUI at once? The answer to that, I believe, is yes, although I actually haven't tested that myself. But if you create multiple simulations under a single project, it should be possible, I believe. Which of the HGS functions are not supported by GMS? That's a good question, and the list of features and functions not supported by GMS is going to be quite long. But in a nutshell, the GMS interface does not currently support any of the additional model domains beyond surface flow, subsurface flow, and the evapotranspiration domain. So that means no fractures, no channels, no pile drains or wells or other 1D hydraulic domains. No solute transport, no density dependent flow, lots of other things as well. Like the list of HGS features and functionality is so long that we could be here for quite a while, but basically we've tried to design the GMS interface around the core functionality of HydroGeoSphere, which again is coupled groundwater surface water flow with evapotranspiration. But again, using the blended method of making modifications to the grok file after using the interface here to develop the initial grok file, then you can incorporate some of those more advanced features. The next question is very similar. Can it simulate density dependent flow and transport? Those implementing these features in the interface is not currently supported, but at the end of the day, you can modify the grok file and run those features um, using that blended approach. Another question is it easy to bring the results to FeeFlow? The answer to that is no. Again, FeeFlow is a completely different model engine. Just like ModFlow is a model engine, HGS is a model engine, FeeFlow is a completely separate model engine. So the results are not directly comparable. Uh, but with that being said, I believe GMS can also be, you can build a FeeFlow models in GMS as well. So you can use the interface to build multiple similar models using different flow engines and then compare the results pretty easily. Okay, now a question from Anner. If I rerun a simulation with the same name from the same folder, but for a shorter simulation time, will GMS consider the old output files when running HSplot? Is there an easy way to clear all legacy output files before rerunning a simulation? That's a really great question, Anner. And the answer is that I believe it GMS will not automatically wipe a folder clean. Michael, jump in if I'm wrong about that. We may have covered that in the design, but I think basically, unless if it's a shorter simulation runtime, then some of those older output files may still be in the project folder. So you'd need to go in and manually delete those. Michael, can I get a fact
I,
check on that?
I think that's right, as I recall what you're saying. Yeah.
So yeah, so if anybody is interested in a little bit more context about that, right, what we would want to do if we wanted to run a shorter simulation, I would right click the simulation, go to simulation controls, and then maybe remove the last output time. But in the project folder itself, we now have binary HGS output files at a number of different output times, 9 of them in fact. So if I do not delete the binary output files from the 9th output time, the one that we just deleted, then those will stick around in the project folder. So we would want to make sure that we remove these before making any changes and then rerunning the
However,
model.
however, we don't just read in everything that's there. We read in what's written in the one file that lists all of the outputs. So
Right.
perhaps that makes it so that you wouldn't actually have to delete the old output files.
That's a good point. Well, why don't we just quickly run a test on this? We can save our simulation. And this may take a minute or two, so you'll have to bear with us if we want to get to the end of this workflow, but we'll give it a test. And in the meantime, we can answer some other questions here. So does GMS support 2D cross-section views based on a defined polyline of interest? I'll leave that question to you, Michael.
We do have cross-section views. So yeah, that is something that we can do.
Awesome. So again, though, I think that's something that you'll probably want to refer to just the general GMS documentation and tutorials about. I'll be including some links in my follow-up email to where you can access different tutorials for both HGS as well as GMS. Okay, I haven't seen any more questions come in. I know that we're 6 minutes now after the hour, so probably many people are dropping off the call. I want to thank everyone for joining me today. I'm happy to stick around for another, however long the questions continue to come in today. But I think at this stage we can probably call it an official end. And we'll just stick around here for another minute while this while this simulation finishes up, and then we can see how GMS handles reading in those new output files. Perfect. Okay, so it finished running, and if I read in the solution now, it's going to tell us we're going to unload the existing simulation output files, which is good. And yeah, so it looks like it actually did. It only read in the most recently updated files. But if we access the project folder, what we'll see, I believe, is that the final output time from the previous model run, those files are still there. So I would still recommend coming in here and deleting them just to do good cleanup of your project files, just to avoid any confusion. Um, but it looks like from a practical standpoint of loading in the model results, it's going to ignore the last output time from the previous run. So hope that answers your question, Anna. Okay. Well, if there are any other questions, you're always welcome as well to just email them directly to me. Otherwise, I think we can call it a session. Thanks again, everyone, for joining me today. And keep an eye on your inboxes for a follow-up email with a copy of this project and a recording of the webinar.